Here's another ODE that looks fairly innocent, but will have some very interesting behavior. So let's get started here. So it's already in the correct format, so our f of x comma y is y plus 1 over x. And so let's go ahead and compute partial f partial y. Okay, well that's partial y of y plus 1 over x plus 1. So we treat x as a constant, so it's really, y plus 1 over a constant. And so on the top here, that turns into 1 plus 0 over x plus 1. And right, that's just 1 over x plus 1. So these both have the exact same problem. There's a divide by 0 problem when x is equal to negative 1. So here we go. So f of x comma y and partial f partial y are discontinuous. Sorry, let me fix that. Continuous at x is equal to negative 1. All right, so that's going to tell us that as long as our initial condition is y of x naught, where this x naught is not negative 1, we'll have a unique solution. Doesn't matter what y naught is, because this discontinuity is dependent on y. Doesn't matter what y naught is, we should be fine. All right, but maybe something interesting happens at x equals negative 1. So we actually can solve this one. This one's a little bit tougher to solve. It is separable, so we're going to go ahead and do that. So this is dy, oops, let me make that a little nicer. dy over dx equals y plus 1 over x plus 1. Okay, well we can multiply by x plus 1 and multiply by, we can divide by y plus 1 and multiply by dx. We'll end up with, what do we have here? dy over y plus 1 equals dx, leaving a space for the integral, over x plus 1. I can integrate both sides. And so that'll give me natural log, absolute value of y plus 1. Okay, and then I've got, what's next here? Equals natural log, absolute value x plus 1 plus a constant. All right, well, let's get to solving for y. So I'm going to exponentiate both sides. So I get e, the natural log, absolute value of y plus 1 equals e to the natural log, absolute value of x plus 1 plus c. But I can rewrite that. So I can simplify the left-hand side first. Oh, let's just do everything in slowly. So natural log, absolute value of y plus 1 equals e to the c times e to the natural log, absolute value of x plus 1. Okay, so the e and the natural log cancel, end up with absolute value y plus 1. I'm going to do this step here. E to the c is another constant, so I'm just going to call that another c. E and natural log cancel, end up with absolute value x plus 1. All right, so I can kind of drop the absolute values, because no matter what they are, c can be whatever c needs to be to get the equation to work. So then we're going to end up with just y plus 1 equals c times parentheses x plus 1. And then solving for y, we end up with, I need the room there, so y is equal to c times x plus 1 minus 1. Well, that doesn't look so bad, but why is it acting so weird? So now let's take a look. This is in a nice format here. So when x is negative 1, the c disappears. So let's go ahead and graph here. So yeah, I'll need a big one. X and y. All right, so we have this vertical line at x is equal to negative 1, and there seems to be some sort of problem on it. And let me draw that a little nicer right there. All right, and if x equals negative 1, this whole bit cancels, and we're at negative 1. So it looks like these lines are actually going through negative 1, negative 1. So that's about square-ish. All right. So it looks like there's something interesting going on with that point. Now if we pick different values of c, we actually get differently sloped lines. So this equation here is actually, it's an equation for a line with slope c going through the point negative 1, negative 1. And so if c is 0, we get a flat line. So That's c equals 0. And it's going to go through this way as well. Sorry, c equals 0. Wrote that wrong. But if c is 1, then we get a slope 1 line. So something like that. That c is equal to 1. If c is negative 1, we get a slope like that. And we get every other line. The only line we can't get is actually this one here, because we'd have to have like c is positive infinity or negative infinity, as the lines get steeper and steeper. So this one, it would be, I can kind of draw this. All right. Oh shoot, sorry, I mixed those up. Sorry, this is positive 1 slope. This is negative 1 slope. All right. So this would be c equals negative 2. And if we went the other way, this is c equals positive 2. And I'll go through there. All right, they can kind of get steeper and steeper as we increase c, but they'll never get to vertical. And they also get steeper and steeper as we decrease c towards negative infinity, but they'll never quite get vertical. But now something weird kind of happens here. When we get to this point, we could, come in on a slope positive 1 line and leave at a slope 0 line, something like that. What's really stopping us from doing that? So let's take a look. That will actually end up breaking the derivative. So we want the derivative to be defined here. So in order for the derivative to be defined, as we approach from the left, it has to have a certain slope. As we approach from the right and left, it has to have a certain slope, right? In order for that to work out, in order for y prime to be defined, at this point, negative 1 comma negative 1, we have to have it continue through the same slope that it started with. And so that's kind of the trick here. So you actually have this weird behavior where, again, you can't get most of the solutions on this vertical line. And you kind of have, it almost looks like an option once you get to this point to go any which way you want. But you do have to be careful, right? Y prime must be defined. Darn, I can't write today. At negative 1 comma negative 1. So, these are valid solutions. Y equals c times x plus 1 minus 1, is a valid solution. Yeah, just double checking. Do I have enough room to plug that in? I might have enough right here. All right. So if we actually plug c plus x times x plus 1 into the original equation, we've got y prime is equal to, it's y plus 1. So y is c times x plus 1 minus 1. But then I have the plus 1 from the original, right? So this y plus 1 over x plus 1. That's the top. And then on the bottom, I have x plus 1. But that minus 1 and plus 1 will cancel, so I'll end up with c over times x plus 1 over x plus 1. So y prime just becomes c. The slope of the line, pretty much, is what c stands for. And so yeah, you can have a solution actually pass through this point. And this is a removable discontinuity. It can go away, but because, it's really, a discontinuity here, removable discontinuity, but still a discontinuity, the existence and uniqueness theorem couldn't tell you anything about passing through the line, the vertical line x equals negative 1. All right, we know for sure we're going to have a solution if we start anywhere that isn't on the line x equals negative 1, but the existence and uniqueness theorem wasn't able to tell us anything about starting on the line x equals negative 1. We actually had to investigate further to determine if there was a solution there, and if that solution could solve the original difference equation. In particular, y prime had to be defined, and plugging in the solution we found, it looks like it worked with a removable discontinuity.